This lecture is an anthology of selected videos that is proposed to be heard to those who can perceive space exploration as the physical extension of our life. The biological implications from the science of genetics, especially for the case of the interstellar travel, is by definition a remarkable milestone and perhaps the next beacon quest as we proceed to recognize our pathways far beyond our planet. This lecture perhaps will be little different and quite extended, in order to present these fabulous storytelling enrichments, from those who are familiar and masters to these subjects. To this video lecture, I would like to keep your attention to the heart of the scenes, from those selected fascinated persons who really make a difference to our cosmos, so to discover what kind of thriving genes are expressed in way, unfolding these stories for how life is transferred in front of you and far beyond.
Before I introduce our panel, to give opening remarks, you should please welcome an astrophysicist, 5-time flown space shuttle astronaut, and head or associate administrator for NASA's Science Mission Directorate. Ladies and gentlemen, Dr. John Grunsfeld.
Space, the final frontier. These are the voyages of the starship Voyager. Its 36-year mission to explore strange new worlds, to seek out anomalous cosmic rays and new plasmas, to boldly go where no probe has gone before. Those words from Star Trek, of course, have inspired so many of us, and I think are characteristic of the excitement and the discoveries we're going to talk about today. Voyager, like the ancient mariners, is pushing out into new territory. NASA's science is all about exploring the Earth, the solar system, the galaxy, and the universe itself.
NASA works by science. O-rings better work, the amount of energy, the thrust needed to lift and free ourselves from gravity, the mathematics involved in setting an arc there because you want to land over there, all that's mathematical. But science fiction is totally imaginative. It's the exact opposite. What happens if light that is bent and you could go through the center and make it quick? All these imaginative exercises in science fiction is merely food for the imagination of scientists who are actually working with technology that is. Imagine sending a vehicle to take a photograph of Pluto and come around and take around and then move around and keep going. You can't do that on a motorcycle. I mean, you set your course on a motorcycle. If you don't hit your line, you're going to fall. Oh, you're taking it around there. It's phenomenal what NASA is doing with science that is, when you look at it, is the equal of science fiction. How are you going to make a parachute that's going to stop a vehicle and it pops out and it's going to stop it? It's not a miracle. How much line do you need? What should the material be? How do you slow it down before and then you got to send a signal, and is it 7 or 9 minutes later the signal? I mean, it's science fiction. Shadows that cross in front of a star that suggest there's a planet. And it's big enough planet to be the size of the M1 of the Earth. Is it possible that life exists on that planet that's only a shadow in a telescope? Those are the imaginative things that NASA are looking at that's every bit as passionately imaginative as science fiction. But you guys are working on it. It's incredible.
Hello, I'm Joe Acaba, educator and flight engineer on Expeditions 31 and 32 aboard the International Space Station, a complex outpost dedicated to scientific discovery, technological development, exploration, and education that orbits more than 200 miles above Earth. During my 6-month stay on the space station, I'll work alongside astronauts from Russia, the Netherlands, Japan, and others from the United States in the most advanced laboratory ever built to conduct physical and biological experiments. Technological advancements being tested in space today will help us develop new systems that can sustain life beyond where we've been before. An increasing number of careers depend on a well-developed knowledge of science, technology, engineering, and math. The nation needs you to help prepare the next generation of problem solvers to be on the forefront of innovations in space exploration, systems engineering, nanotechnology, and countless other fields that help improve the lives of people on Earth. The first person to walk on Mars could be someone you inspire. Learn more about NASA resources that can help you spark student interest and ignite lifelong learners at nasa.gov/education.
Voyager 1 has left the bubble around the sun and entered interstellar space, the space between stars.
It's amazing that Voyager has operated 36 years. Launched in 1977, traveled past the gas giant planets, and now off into interstellar space. A radio telescope took a radio image of the Voyager 1 spacecraft, slightly over 11 billion miles from the Earth. And it's a very small radio dot amongst a sea of darkness.
We have an instrument on Voyager which can measure the density of the ions, the plasma which is out there. In March of 2012, it turns out there was a massive eruption from the sun which eventually reached Voyager 1 in April of 2013. When that blast wave reached Voyager, it caused the plasma around Voyager to vibrate or oscillate in a certain particular tone. Literally, they're the sounds of interstellar space. And by measuring that sound wave, we could measure the density of the plasma, and we're amazed to find out that we were in interstellar space. This is a historic milestone in the great journeys of exploration that have been undertaken by humankind. Well, it is quite remarkable when you think about it, that far off now at ever increasing distances, there's this little vehicle, 2 of them, which were built here many years ago and launched 36 years ago, now on a journey that will basically last for billions of years.
Here's the dilemma. We know how to get to relativistic speeds in laboratory. We do it all the time. And then we go to the macroscopic level, where things like aircraft, cars, spacecraft, we're pathetically slow. So the question is, can we bridge that gap between what we do now on the macroscopic level with chemical binding energies to relativistic speeds, which are done with electromagnetic acceleration? The shuttle, when it would take off, or the SLS, when it will take off, will have a power off the launch pad of between 50 and 100 gigawatts. Turns out, to get to relativistic speeds with the spacecraft we're talking about, you need basically the same power level. And for about the same amount of time. It takes 10 minutes to get to orbit with shuttle. It takes us 10 minutes to get to 30% the speed of light with about the same power level, just using different technology. We could propel a 100-kilogram robotic craft to Mars in a few days. If you want to push something like shuttle class, it takes you roughly a month to get there. Within about 25 light years of the Earth, there's actually quite a few potential exoplanets and habitable things to visit that may be habitable. We don't know, of course. And so there are many targets to choose from. The closest is Alpha Centauri, which is about 4 light years away. So photon-driven propulsion is not a new idea. It goes back to the beginnings of thinking about light, in both the classical and the quantum mechanical way. There are recent advances which take this from science fiction to science reality. There is no known reason why we cannot do this. There's a roadmap, which you can look at in our paper, to relativistic flight. The system is completely scalable modular, built any size you want, from a tiny one to a gigantic one.
I'm working on a form of nuclear power that's apparently very clean and very scalable. In working here at NASA, you're exposed to a lot of different things. And I became aware of a new theory, a Whittam-Larson theory, about 3 years ago now, that appears to explain why you can use the weak force to get at nuclear power in a completely different way. I had been working with Lewis Larson, one of the authors of the paper, to understand the theory. The way that we're looking at this is to take and add just a neutron to an element, increase its mass slightly, but there's binding energy involved again. That's released in the form of nuclear energy. The key here is, how do you produce the neutron? And that's the exciting thing that's been becoming more and more evident in the work from the past 20 years that people have done worldwide. What we're trying to do is a physics experiment to understand whether the Whittam-Larson theory and its predictions are at least in part correct. We made a little device, 1.5 centimeters wide by 2 centimeters long, comprised of these little tiles. Each tile is a separate test device, and we have 48 different experiments that we can run simultaneously. We run an experiment on this entire thing, and we see how this square compares to the one next to it. And so it becomes a differential measurement. The tolerances for making a good differential measurement are greatly reduced. The other thing is uniformity. We process this device the same, and it accelerates the science we do as well, but makes it easier. The interpretation of the data is much more direct, and the criticisms that have been levied against previous attempts aren't valid in this case. We got to work with a small company on a study to see whether we could do something that's been desirable by NASA for a long time. That's a single-stage, fully reusable space plane, a rocket, something that could take a reasonable sized payload to orbit and return without shedding any parts. So when you fully grasp what this represents, a very inexpensive, clean form of power. If we were to have such a thing, it would be the sort of technology that would fuel our future growth and expansion and have the ability to raise the standard of living of the entire world.